Hi, and thanks for watching this video about my Homebrew computer. This is a 2024 update because although I've got quite a few videos on my channel about my machine, some of those videos are pretty low quality. So I thought in 2024, with better AV hardware and software, I can do an introduction and overview that is a little bit more informative and interesting for people. So without further ado, what you can see here is the Homebrew. It obviously looks like a BBC Micro, but it's clearly not. But it is housed inside a BBC Micro case, and I use the BBC Micro keyboard. So if I take the case off, what you see underneath, or rather inside, is the Homebrew computer. It's all based on breadboard, so it's a big mess of wires, but it all works pretty well. So I'm going to quickly switch the machine on. I'll just reduce the size of this video feed and turn the machine on, and you can see that the computer has its own software, and I will talk about that in a minute. But first, let's go back to the hardware and explain what's going on here. So this is a 65 CO2 based Homebrew, inspired by the computers that I saw and used when I was a teenager back in the early 80s. And when I read about pioneers like Steve Wozniak and Sophie Wilson and Steve Ferber in the UK, I was awestruck by their achievements. Fast forward 30 years and more with the internet, there's so much information out there that I thought it was possible for someone like me who's not an electrical engineer to be able to actually design their own computer. I have a background in embedded software, low-level software programming, so I thought I could handle that side. But to design my own hardware became in reach thanks to all of the excellent information available on the internet. So I was inspired by a number of homebrew machines on the internet, but this is still my own specific design. Even though there are some great creators of homebrew machines out there, I wanted to make something that was quite different in the sense that this is a machine that is a fully capable microcomputer rather than a single board homebrew which had maybe serial I/O. I wanted something with video, with sound, with joystick capability that could sit alongside the computers that I used to play around with in the shops back in the early 80s, like the Commodore 64, the Atari 800, or indeed my first computer, the Oric 1. So let's go through the hardware. I'll just move I've just moved the keyboard out of the way so we can get a better view of what's going on here. So here we have the 65 CO2, obviously the heart of the system, and it's powered from a clock circuit here, which is there's a 21.7 megahertz master clock, which is divided by 2 for the video, which I'll talk about in a minute. But it's divided by 4 to give me a 5.36 megahertz clock for the 6502. This is a modern part made by Western Design Centre. The CEO of WDC is Bill Mensch, who was one of the original team of the 6502. Then alongside the 6502 you need the peripheral support chips. So you have a 6522 VIA here, and there's another one just under this keyboard ribbon. This 6522 controls mainly the keyboard interface to the BBC Micro, and also some lines here which go to the address decoding circuitry to help with accessing more than 64K of RAM, which I'll talk about in a minute. The 6522 under here, I can't really show it very easily, under the ribbon, is used for controlling the sound chip, which is a AY38910. This is the same sound chip that you would have found in the Oric 1, but also variants or similar devices in machines like the MSX and even the Atari ST, and also the Spectrum Plus models, I believe. The video is generated by the Texas Instruments TMS 9918A video chip. This provides 256 by 192 high resolution graphics, as it would have been called back in the day, along with 15 colours and also 32 hardware sprites. Now, considering this chip came out in the late 70s, it's a pretty powerful chip. It outputs composite video directly, so I can easily put it, port it, or not port it, route the signal directly to a monitor, and I've just got a video capture card here on my PC that shows you that. So it's a pretty awesome chip considering its age. On top of that, I have this additional mess of wires on this, let's call it a daughter board. Here I have a 6551 serial chip, and I'm going to show the serial chip in a short while. Before I got the video working, I needed some, and the keyboard working, I needed some way of being able to read and write input output to the machine, and as is the way with a lot of homebrew computers, serial is one of the simplest ways to do that. So I've got a terminal, TerraTerm, on the PC linked up to the serial port of the homebrew, and this is the chip through which that communication is done. Over here you've got just the power circuitry. I used to use a 7805 5-volt regulator, but now I've got a switch mode power supply kindly given to me by a fellow hobbyist at the Cambridge Computer Museum exhibition in November. All of the parts are period parts, apart from one thing that I compromised on was storage. So here there is an SD card. The SD card is actually driven in software, the SPI protocol, through the 6522 that's behind this ribbon cable. So I do software bit banging of the SPI protocol, and I've also then implemented a FAT16 file system to be able to read and write standard files to the SD card, which I can then easily transfer between PC. The other chip I've shown on, I've not really talked about, is the Dallas DS12887 chip here. That's the real-time clock and calendar. You can see from the boot up message of my homebrew that there is a problem, which I'll have to try and get around to fixing. It was working, but don't know what's happened in the last few weeks. That's about it from a functional point of view in terms of hardware. Just to explain then the ROM and the RAM. So behind this daughter board is the VRAM for the TMS chip, and that's 16K of VRAM, which is accessible only through the video chip. Then the 6502 itself has access to a 128K of RAM, which is under, there is a RAM chip under here, a static RAM chip, 128K, and I've also got a 64K EEROM. Now that adds up to way more than the 64K of addressable memory that the 6502 has. So as I mentioned earlier, the way that is decoded is through the address decoding scheme, which basically decides whether I'm accessing RAM or ROM or I/O space. In addition, I have 4 pins, which, depending on what I'm accessing, is, let's say if it's ROM or RAM, these 4 pins then are providing address lines to swap in the appropriate bank. So I am using 4 banks of 16K in the top of RAM for the EEPROM, and then the rest of RAM, the other 48K, minus the I/O space, is for a volatile memory, but I can swap in 32K banks there as well. So I can access all of the ROM and the RAM space, minus 4K space for my I/O. That's the hardware. I've got a couple of stickers, proudly declaring the use of 6502, and also it's all 7400 series logic here. No programmable devices or anything complicated, just all the decoding is done using 74 chips here, and there's just some extra decoding here for the I/O space. The clock circuit is just, again, 74 chips with the counters to divide down the clock for the different different chip requirements. So that's the that's the PC hardware, that's the microcomputer's hardware. And as I say, I wanted to build something that was going to be able to sit alongside the consumer microcomputers that we had back in the 80s. So that meant writing a lot of software. You need to have a basic, and behind the basic, you need to have input output, a small set of, let's call it operating system type kernel drivers for your keyboard, your video, your sound, your serial, your file system, and even the real-time clock when I get it working. So all of that had to be written, and as part of this project, which for me was an exercise in discovery and personal learning, I wanted to build everything from scratch. So this is my own design hardware, but also the software is my own design. The main part of the software is a basic programming language that I created called D-flat. So D-flat is a joke on C sharp. But as you can see, syntax error +6, it is a high level language, and on top of that high level language, or alongside it, I have a file system, as I mentioned, FAT16 file system. So I designed and built my own computer language called D-flat, and I implemented a FAT16 file system with the SD card so I can easily access files and exchange them with a PC. And if I go to, let's say, the demos folder, I've written a few demos. Let's load one of them, circles, and then I can maybe show the program. So you can see it's basic like list, etc. One thing that D-flat has, which I'm not showing here, is not only is it a high level language, but it also gives you access to inline assembly. So you can mix assembler and D-flat, even exchanging and using variables between the two languages. A little bit like BBC Basic, if some of you I'm sure will remember that. So what have we got here? The line numbers make it look like a regular basic language, but there is no go sub and go to, so you have to basically program this using a procedural approach. So everything is a procedure. So right at line 100 we have the definition of a procedure called start, and at the end you have the end definition of the procedure, and in the middle there is the code to do various things. So there's no go to and go sub, as I said, but you can do repeats until, so line 120 to 266. You can do for next loops, line 130 to 260, and basically it should be quite familiar to those of you who have programmed in BASIC, or maybe even something like Pascal will feel quite familiar. So let's start this. What I want to show is that this version of BASIC I've created takes advantage of, or can exploit, the hardware of the computer. So if I press enter, it goes into high resolution mode and draws 50 circles in a random position and colour. If I press enter again, another 50 circles. So you can see that 5 MHz 6502 is actually quite speedy. D-flat is integer only, so that helps with the speed of the language, but it also shows that how fast almost like a RISC-based architecture of a 6502, simple instructions but don't take too many clock cycles to execute, how it can provide a good amount of performance for what is quite a low clock speed of 5 MHz. So that's my computer showing off from the point of view of using D-flat. Let's go into serial, and my keyboard just dislodged, so I'll just put that back if I can. Yeah. Now, in terms of the serial, then I've just pressed F1 while pressing reset, and that tells the startup code that I want to use serial as my keyboard and screen rather than the actual physical BBC keyboard. But I can still do the same things here. So I can do dir, I can do the good old print hello over and over again. So the usual kind of things we might do in W.H. Smith's. Let's break into that. Now let's go into the demos folder again. Typed it in wrong. Let's have a look what's in here. There's something called Snowman. I'm gonna, even though I've shown Snowman before, just want to now put it here so we can just do a quick rundown about what's going on here. So if I list this out, the good thing is on the terminal I can scroll back through and show you what it's doing. So there's an initialization procedure that's loading something that's called Snowman, which is actually a picture that I've generated on the PC. And then I've got some sprite data here, and I've got some music data, and well, let's just start it using the start procedure. I'll invoke it, and now you'll see the Snowman and playing the Snowman theme from the Channel 4 program that comes on every Christmas. And I know it's not Christmas, it's now February, but it shows a little bit of what you can do with D flats quite easily. Let's stop that if it gets annoying. And then the final thing that I wanted to show is, let's reset this again back to the regular boot up sequence. Let's change directory to games. And one day I'll be able to actually type and talk, but not today. So here I've got my usual demonstration, and Tetris 2 is a slightly updated version, which is a little bit more fancy in terms of its graphics. But you can see the SD card flashing away. It's loading each block 512 bytes at a time. That's raw text that's being then tokenized by D-flat. D-flat is a tokenizing interpreter to help with speed, and then it's now ready. So let's list this out so you can just quickly see what it looks like. It's a structured language, so you can put comments in. You've got different procedure names, etc. Your high-level calls like plot, which allows you to plot a graphic at a certain place, and also sprites and sound commands. This is one that's playing music. So you get the gist. So let's start it. And this game uses the joystick. So I have my joystick, another 80s classic zip stick, and this is all in D flat. So let's play it so you can hear the tune. I'm using the joystick to control the shapes. So this is D flat doing Tetris, and I guess I think it looks okay. I think it plays fine. The speed is good. This is obviously on the lower level, so it's by definition going slowly. But when it speeds up, it can go pretty fast. So that's Tetris. Let's reset that, otherwise the music will get annoying again. And finally, let's go back to the serial. The good thing about using the serial ports is that I can maybe go into high resolution mode. Let me just change the border color so it looks neat. And I can issue high resolution commands and actually see what I'm doing, because if I did it without the serial, then I'd be blind typing essentially. But I've got commands like line, which can allow me to draw a line, as you would expect, or circle. And to get an idea of the speed, let's do circle from 3 to say 70 in steps of 4. Let's do circle 80, 80, A. I mean, that's quite quick. I think it's way faster than my Auric was. And then one other final thing, as I talked about sprites, I have a sprite handling commands as well. So set sprite 0 to coordinates, let's say 100, 30, ASCII code 65, which is an A, and then the color 4, which is a bluish color. And I didn't type that correct because it's not sprite pos, it's sprite. And that also shows that I can't remember my own language sometimes. There's the A, and we can animate this A now, so let's just do that very quickly. X equals 0 to 255, in steps of 1. I can use sprite pos this time, and I'll use it at position 30. And then if I type wait 1, that waits 1 vertical blank period, then the next X, and then until 0. So if I do repeat until 0, it means it'll carry on forever, of course. So that shows that in D flat I can access sprites and I can move them about. I can do that on a high resolution screen. So that's about it for this introduction for 2024. I'm going to redo some videos and go deeper in both D flat and the hardware. So if you have any comments and you want to know more, I'm certainly interested to hear what you'd like to look at next. But thank you very much for watching this video.